sklearnPipelinePipeline. Description: the pipeline class in scikit-learn sklearn provides a way to chain multiple estimators, e.g., transformers and classifiers, into a single sequential workflow. This allows you to streamline the process of data preprocessing, feature engineering, and model training, ensuring that these steps are executed in the correct order. Pipelines are particularly beneficial for improving the organization and reproducibility of your machine learning projects. Inputs. Data: the input to a pipeline is typically a dataset, usually represented as a NumPy array or a pandas data frame, containing features and labels for supervised learning. Estimators: pipelines are composed of multiple estimators, which can include transformers, feature extractors, and/or models. These estimators are specified as steps within the pipeline. Outputs. Transformed data: if the pipeline includes transformers, the output will be the transformed data after passing through all the transformers. Model: if the pipeline contains a model as the final step, the output will be the trained model. Predictions: if you call the predict method on the pipeline, it will return predictions based on the trained model. Steps. Transformers: transformers are estimators that modify the data, often for feature engineering or data preprocessing. Some common examples include: standard scaler standardizes features to have zero mean and unit variance. One-hot encoder converts categorical features into numerical ones using one-hot encoding. PCA performs dimensionality reduction by projecting the data onto principal components. Estimator model: the final step in a pipeline is typically an estimator, which is a model that learns patterns from the data. Examples include logistic regression, a linear model for binary classification; decision tree classifier, a tree-based model for classification; random forest regressor, an ensemble model for regression. Metrics. Accuracy for classification problems. This metric represents the proportion of correct predictions. Precision: the ratio of true positives to the sum of true positives and false positives. Recall: the ratio of true positives to the sum of true positives and false negatives. F1 score: the harmonic mean of precision and recall. Mean squared error (MSE) for regression problems. This measures the average squared difference between predicted and actual values. R squared: a measure of how well the model explains the variance in the data. Visualization plots. Confusion matrix for classification problems. A visual representation of true positives, true negatives, false positives, and false negatives. ROC curve plots the true positive rate against the false positive rate for different classification thresholds. Precision recall curve shows the trade-off between precision and recall for different thresholds. Feature importance plots visualize the relative importance of features in a model, helping to understand which features are most influential in making predictions. Fine-tune parameters. Hyperparameters of estimators: the parameters within the estimators used in the pipeline can be adjusted to optimize model performance. Pipeline structure: you can experiment with different combinations of estimators and their order within the pipeline. Uncertainty methods. Confidence intervals for regression problems. Confidence intervals around predicted values can be calculated to provide an estimate of pay. Uncertainty in the prediction. Prediction probabilities for classification models. The probabilities associated with each class prediction can provide an indication of the models. Confidence in the prediction. Ensemble methods using ensemble techniques like bagging or boosting can reduce the variance in predictions, leading to more robust and reliable results. Challenges and fixes. Challenge 1: data leakage occurs when information from the testing data is inadvertently used. during training, leading to overly optimistic performance estimates. Sample use case: if a feature transformation is applied before a model is split into training and testing sets, it's possible to use information from the test set in the transformation, leading to leakage. Fixes: fit transformers only on the training data and then apply them to the test data. Use the column transformer to apply different transformations to different subsets of columns. Challenge to pipeline complexity: as the number of steps in a pipeline increases, it can become harder to debug and understand the workflow. Sample use case: having a complex pipeline with many transformers and models can make it difficult to identify the source of errors or to interpret the results effectively. Fixes: use smaller, modular pipelines to break down complex tasks into manageable components. Implement logging and monitoring to track the data flow through the pipeline and identify potential issues.